introduction for everyone. Got it. So today I'm going to talk about my work that I have done during my PhD in University of Tokyo about physics-based modeling and numerical simulations of mechanics or plastics on non-planar forms. So I'm a postdoc at Stanford University as Taka introduced. So let's start. So I basically talk about two different but related topics in today. So the first part is about main shock and aftershock sequence simulations in fault network, which is published last year with this collaboration with Ando, Ryosuke Ando, who was my PhD advisor. The second topic is the frequency of rupture termination at fault bands. So this is still ongoing work. So let's get started with the first part. So for the introduction, I'm showing the distribution of aftershocks from some continental flexible earthquakes. So for example, in 2000, Western Total earthquake in Japan. So this is the hypocenter distribution. The color is this hypocenter distribution relocated by the mode difference method. So they are very, very accurate in terms of relative locations. And if the location is accurate enough, aftershock distribution can tell us information about fault geometries. So in this case, we have a lot of terrain or lines from this figure. So many people are actually using the geometry and the distribution of aftershocks to infer the geometry of the fault, assuming that these aftershocks are occurring on the same plane, same single plane or multiple planes. But actually, I want to point out from some observational papers that majority of aftershocks are actually of fault events. The reason is given by Yukitake and Yo 2017. So even if we think about the observational error, inherent observational error, the typical width of aftershocks is much larger than typical width of fault zone. The second reason is that many focal mechanisms of aftershocks are inconsistent with the main shock fault plane inferred from this plane and also focal mechanism of main shocks. So this is explaining the idea here. So this is showing p-axis of aftershocks and also locations. So they are diverse, and it's difficult to think all of these events are happening on the same plane. Even non-planar structure of fault is considered probably. So, and this of fault aftershock idea is also consistent with geology, because if you look at the outcrop of faults for trace, there is a single main fault that has a lot of slip, but there are numerous number of subsidiary faults that is surrounding the main fault, which is called damage zone. So it's very easy to imagine that many aftershocks are happening these blue faults, not red main faults. So you can ask a question at any time if you want.
So I can try. What is the main shock in the Yukitake-san's? What is the main shock?
So main shock is too big. So actually in this figure, so
right.
This figure is showing only the southern part of the main fault. So main shock fault is much larger than.
Oh, okay. You are zooming.
So I'm just zooming.
Okay,
so
got
this
it.
is the southern end of the aftershock regions of that earthquake.
Thank you.
So we are having aftershock everywhere, basically everywhere on the fault plane. So any questions? So I can go. So another problem, maybe physical problem about aftershocks is their locations. So classically, in theory, triggering of seismicity is enhanced only if a fault is subject to positive Coulomb stress change, like explained from this figure. So Coulomb stress change is defined like this, as you are very familiar with. So, and if you have a one fault, this fault, and this fault slip here, that you can calculate the change of Coulomb stress by the strip of this planar fault. And the Coulomb stress increases only at the tip of the graph of the fault because there's a stress concentration. And inside of the fault, like fault region and this region, basically Coulomb stress changes almost negative for many different types of fault orientation, receiver fault orientation. So it's really a little bit surprising that aftershocks are actually happening everywhere on the fault, as you see from this type of typical aftershock distribution. So there are many ideas explaining how we have aftershocks in such shadows. And one idea that I'm using in this modeling is fault geometry. So this is the geometry of the outcrop of Corona Heights faults, which is located in San Francisco. So if you looking at the fault closely and measuring the topography of the fault, actually the fault is very rough and non-planar, not perfectly planar at all spatial scale, from small scale, tiny scale to large scale, like kilometer or continental scales. So this rough geometry of natural faults can be mathematically described as a fractal concept. And if you consider fault strip on a fractal geometry fault, you have a very small scale heterogeneity in Coulomb stress on its surrounding. So this is the figure from Aslan and Dove 2018. So as you go close to the rough fault, the stress heterogeneity becomes larger and more smaller scales. So, which means in the proximity nearby the fault, rough fault, there are many places having positive Coulomb stress changes instead of negative because of this heterogeneity or perturbation due to the rough fault effect. So this explains. So from this consideration, we can hypothesize that stress heterogeneity coming from fault roughness causes aftershocks on subsidiary faults in the damage zone of the main fault. So this idea is not very new, but our purpose of this study is putting this hypothesis into a physics-based numerical simulation for step sequence, which is a quite wide community in modeling community of step science. So let's just talk about. So I now turn to the problem setting of my numerical simulation. So this is the fault geometry. So we have examples. It's okay. So we have this sort of fault geometries. So there's one main fault which is red fault. This fault has a fractal geometry, so it's not perfectly planar. It has a roughness. And there are 600 subsidiary faults. And their lengths are 0.6 kilometer uniform length distributions. So this is very ad hoc, but actually we tried many different length distribution of these subsidiary faults in my numerical simulation. And the size distribution is not very important in the result follows as what I talk about before. So the initial condition is so in this simulation we try to reproduce main shock and aftershock sequences. So initially the initial stress on the fault are resolved from spatially uniform stress tensor, and this fault overall fault trace is optimally oriented in terms of Coulomb stress. So sigma 1 is 30 degrees against this fault trace, and the state variable in the latency friction is fixed. I have some method, maybe I shouldn't talk about that. So, and we artificially nucleate north main shock on the center of the main fault. and the main shock propagate through all of the main fault from here to here and here. Then, after some time delay, some subsidiary faults go to produce aftershocks because it's favored to do so. So, the numerical method that I'm using is boundary element method based plastic cycle simulation, so there's a long history of plastic sequence or plastic cycle simulation on latency friction. So this is starting from Zia and Rice, 1986, and there are many papers. So my methodology is one of the most popular and computationally efficient one, especially for nonplanar problems. So there is an integral equation for the elastic stress transfer. So if one part of fault slip, this slip affects the stress in another point. So there is a convolution or integral describing this interaction, remote interaction of stress via Green's function. So this equation, elasticity equation, is coupled with latent friction, which governs the friction, which determines the frictional boundary condition on each point on the fault. Even like this. This is also very popular way for plastic simulations. So because my modeling is much more complicated compared to other simulations, because I'm discretizing not just this main black hole, but also all of these small holes into small enough elements. So the computation, the number of elements are very big actually, even with these 2D simulations. So that for 3D simulation, it's even problematic. So to be able to run this very large scale problem, I spend a lot of time in my PhD, in developing computational software, which is open source. And we accelerate this method in multi-core supercomputer in parallel environment by utilizing a lot of methods, which is recently out in GGI, so you can take a look at that. And also the source code is also available. So anyway, so this is our numerical method, and this is the result I'm talking about the result. So first, I'm showing the evolution of the maximum slip rate on either main fault or these small subfaults, subsidiary faults. So the vertical axis is this is the maximum slip rate, and you can see that the duration of main shock is here is around 100 seconds for this case. So this was artificially nucleated on the stress perturbation at t equals 0. So this completely ruptures the main fault. Then the slip rate decay over time. And after the main shock is terminated, there are many spikes in the slip rate, maximum slip rate in subsidiary faults, each of them corresponding to the aftershock of.
So in your model, is there also dynamic triggering happening, right? Because even if you have a straight fault and a stress shadow afterwards, if you have dynamic wave propagation as part of the model, you would also trigger a few events potentially.
Yes, that's actually happening during the main shock. So there are many changes in slip rate. But it seems in this simulation, it's not very efficient to cause dynamic triggering, because maybe it's because the passage of the rupture front is a relatively short time scale phenomenon. So they have a stress perturbation due to the crack tip, but the stress immediately drops after passing the stress shadow. So the time scale is not enough to nucleate a rupture. It depends actually on the parameters. If some parameter like the sub C is very small, they tend to be ruptured during the main shock.
Mhm.
So they are more like fault damage, which is also modeled by many people. So it depends on parameters and certain
Right.
values. So, but majority of aftershocks are happening after the earthquake, after the main shock, like this plot. So typically, we have 600 small faults, but only 10 to 20 faults produce aftershocks because most of them the stress propagation from the main shock is not large enough, not high enough to trigger aftershocks.
But also the orientation was random, right? Your case.
Yes.
So maybe even though the stress is high, but orientation is different, it doesn't rupture.
Yeah, it's also the problem. So for most faults, the orientation, because the orientation of secondary faults are random, and so if the orientation is optimal in terms of the background stress field and also the stress propagation from the main shock, it can generate aftershocks. But in most cases, they are not optimally oriented to the stress field. So that's another reason why there are relatively minority. So the reviewer talked about a lot about because the editor of this paper is from geology. So they suggest me a lot about the orientation distribution of the secondary faults. Because in field, this is not the orientation distribution of this project doesn't look like random. So this is another point that is not considered in the model for simplicity. Thank you for comment. So I talked about this. So there are some slow aftershocks. So they triggered aftershocks, but the sleep rate during aftershocks is not high enough to be seismic. This is actually sometimes happening. And this figure is showing the cumulative sleep on the main fault and the secondary faults. The main fault, so you can see that after sleep is very small in this plot because this is the end of main shock. And after that, the cumulative sleep is almost constant. Although they are decaying like after sleep, the only like decay, but their absolute amount of sleep is very small. That's why I want to argue that this model doesn't capture after sleep or post-seismic sleep. Because in this numerical simulation, the friction is velocity weakening everywhere, and there's no velocity strengthening location, which can generate after sleep. So this enable after sleep had to happen to solely focus on the interaction between earthquakes, not aseismic sleep in this simulation. So this is showing the spatial distribution of aftershocks and Coulomb stress change due to the main shock sleep, solely main shock sleep. So as you already see from another paper that I introduced, the Coulomb stress field for optimally oriented fault is very heterogeneous on the nearby the main fault. So there are a lot of positive Coulomb stress change regions nearby the main fault. And the black dots are the location of aftershocks. They are matching very well. So that means I can argue that the aftershocks are generated by Coulomb stress. Like aftershock distribution can be explained by Coulomb stress idea, although it's very difficult to really observe this sort of very small scale heterogeneity in Coulomb stress from natural observation because it depends on the very small structure of fault geometry, which is not accessible. So So again, so I just want to repeat. Aftershocks can be explained by Coulomb stress, but it is impossible we know such small scale heterogeneity for the geometry. So that's why we apparently see aftershock distribution doesn't correspond well to Coulomb stress distribution, computed from very simple assumption of long wavelength assumption for the geometry. So I'm doing a little bit about parameter study. So one very important parameter in this model, in this simulation is alpha, which is defined as the ratio between length of the port, 100 km here, and deviation, mean deviation from planarity. So alpha equals 0 means flat mean fault. So in this case, there is no aftershocks inside the main fault, and all of the aftershocks are happening at the crack tip, post crack tips. But as increasing the roughness, the alpha parameters, you tend to get more aftershocks inside the fault zone and less aftershocks at the tip. So this increase of all aftershocks here is because stress is more heterogeneous due to the more complex geometry. So there's a more chance to getting positive Coulomb stress.
How different is the slip distribution? Is it just more ragged, but still the same?
So it's very good point. I have one extra figures explaining the slip distribution of different alpha. So basically, we tend to get smaller value of slip if you increase alpha parameters. This is because it actually can be explained by theoretically in terms of roughness drag theory, which means if fault is rough, there is additional shear resistance acting on the fault against slip. So there is slip is not preferentially occur in rough.
Are you reducing the moment then by increasing your roughness?
Moment tensor?
Are you reducing the magnitude by
exactly.
So shouldn't that affect your aftershock productivity as well?
Yes, that's the point. So
That's why K on the outside.
So actually that's why we tend to get smaller number of aftershocks
In the tip zone.
because this is basically determined by the stress concentration from the main shock. It depends on the magnitude. So this is a spatial variation. We have talked about the spatial distribution of aftershocks, but we can also investigate temporal decay of aftershocks, which show very good agreement with Omuritz's very famous Omuritz's law, which states that aftershocks per time decay at a power law type function. So this is showing the decay of aftershocks. They are power. They look like very powerful. And so I changed in this left panel, I changed initial state variables of subsidiary faults. And if their state variable, initial state variable is high, the aftershock duration tend to be get longer. And in the right panel, this is varying the initial shear stress. And if the initial shear stress is higher, they tend to have a more productivity. So this is kind of some parameter studies. But the point here that I want to argue that it's not very surprising to obtain Omori law in this simulation because Omori law can be theoretically derived from latent state friction and the sudden jump of stress, which was shown by the 1994. But it's not that trivial because many assumptions in the 1994 are not valid in our simulation. Like stress heterogeneity, so they are showing uniform stress, but we have stress heterogeneity for sure, and interaction, so this finite size, and some approximation in solving the equation analytically. So it's not very trivial. And their paper also say that the C, time constant, it depends on frictional parameters and stress. But in our simulation, we cannot see time constant. So the time taking to initiate the power law decay time constant is not seen in our simulation. So this is one difference of our result from detailed theory. The p-value is 0.9 for most simulations.
Are all the abstracts of the same magnitude?
Basically the same because the size of the fault, the secondary fault is same, basically same. But I also try some set of simulations using the power law size distribution of secondary faults. In that case, we get Gutenberg Richter, but it's not very interesting because it's a very general trivial result. So I think I have some figure in the appendix. Yeah, like this. So this is the Gutenberg Richter distribution for constant size distribution. So this is more like exponential cumulative distribution. But in this case, I have a power law size distribution like this plot. In this case, we have more like power law size distribution.
Yeah, thank you. Because in the beginning, you showed that all the secondary faults are the same. Then so I was curious the magnitude of the abstracts.
Yes, it's very good
Thank
point. So this is about temporal characteristics. So I move on to the migration of aftershocks. So this model can also explain the migration of aftershocks over time. So in observations, there are many observations that the region of aftershocks expand log time, logarithmic of time. So it can also be reproduced in our simulation. So this is showing the time and location of aftershocks from the tip of the fault. So this is the fault tip, and as we move away from the fault to increase the x values. So the points, this point showing the location of aftershocks. So you can see that aftershocks location is expanding over time. So the mechanism of expansion of aftershocks here is as follows. So as we move away from the fault edge, so there is a stress concentration around the tip of the fault, and it decays with distance from the tip. So stress decreases like square root singularity from the basic idea of fracture mechanics. And in the latency friction idea, the time to nucleate an aftershock depends on the initial stress, and it's decreases with increasing initial stress. So if we have smaller stress, it takes a long time to get instability. So this combination explains the apparent migration or expansion of aftershocks. So this is not coming from a seismic slip because we disable a seismic slip in this model. And we also we don't have a fluid too. So we can argue from this observation that migration of aftershocks does not necessarily mean a seismic slip propagation or fluid diffusion. So there's also some semi-analytical solution to explain this migration. Also, it's not very accurate in some limit, like long-term limit and small-term limit. So this is, I think, one interesting observation from our simulations.
Can I ask one question? In the Kato Obara-san, you can see the migration speed is different, right? What's your speed here in the equation? Where we plug into the migration speed in the
So it's very difficult to compare, quantitatively compare.
Okay.
And this is actually very extreme case because the migration distance is much larger than initial fault size.
Sure.
So this is a very kind of extreme case. And I think in most cases, like Parkfield earthquake, there's one paper about aftershock expansion from Parkfield earthquake. The migration distance is more or less the same as the main fault inside.
Right. Because my question is usually, seismicity, we can get to the migration speed, right? Something calculation number is, 10 meter per second, something.
Yeah.
I just wondering the left, your simulation, where we can compare.
We haven't.
Is it? There's no number for the migration speed?
So it's very difficult to define migration speed because its migration speed is not constant. It's decays over time because this is log time, logarithm of time,
Okay.
and this is a linear coordinate. So
Okay.
it's decreased with time. So I think we can define the migration rate by 1 kilometer per decade or something like that as a baby.
Okay, I don't want to spend time for my question, but if you want to speeding up for the migration speed in the left, which parameter we should change it? Okay, I want to produce, because this is a typical one migration speed, right, in your simulation.
Yes.
If I want it, speed is very small or very slow or very fast, which parameters typically can be changed?
So A is the direct effects in the latency deflection. So it's more or less material constant.
Okay.
So it cannot be changed that much. Sigma is effective normal stress. So it depends on many tectonic settings for depths.
Okay.
So it also depends on the power fluid pressure. So if power fluid pressure is high, its value becomes very small. So migration is much faster.
Oh, okay. Okay. So we can kind of combine together.
Combine the many parameters.
Thank you.
Yeah, you're welcome. So I spent like 30 minutes now. So maybe I should switch to the second. The other is not very important. So the part 2 is about frequency of rupture termination at fault base, so which is dealing with more longer time scale. Because in the part 1, we only focus on single main shock and aftershock simulations sequences, so relatively short time scale. But if we think about the dynamics of non-planar fault for long time scale, what happens is the question. So in natural earthquake observations, rupture arrest location, rupture termination location often correlate with the fault geometry. So this is a paper from King and Nabel 1985. So relatively old paper that is already showing some correlation between fault geometry and the location of rupture arrest. So more recent paper about the Magyo earthquake in China also document that the both edge termination location of strike slip faults correspond to the change of fault strike, which is bend. So this is a kind of case studies, but in 2017, Bayesh and Wesnowski quantified and doing statistics about this phenomena. So they obtain empirical relationship between the angle of fault bend and the ratio of the probability of a rupture arrest. So they are using more than 50 past strike slip ruptures all over the world to quantify this. And the finding is that first, the probability of rupture passing a bend decreases with increasing bend angle. The second is the bend greater than 45 degrees almost always stop rupture propagations. So this is very interesting observation. So we wanna reproduce or can we explain Bayesh and Wesnowski empirical law by physics-based modeling that I already talked the framework earlier. So the program setting is like this. So we are running earthquake cycle simulations based on the latency deflection as the same to part 1, and we add loading because we need multiple earthquake cycles in this chapter. By adding, we add loading by placing creeping segments at the both extension of the fault, like this and this. So you can see the creep, constant creep here, the stress increase due to the creep, stress increase here and also here. So they tend to nucleate proceed at some intervals, depending on the loading rate and the size of the fault. And so that to explore the effect of fault bend, so we put bend here. So two planar segments are smoothly connected via restraining or releasing bend. Restraining bend is here, and releasing bend is this. So we are basically running many multiple aspect cycle simulation using this geometries. But one important problem in nonplanar cycle simulation is normal stress changes. So you can imagine that if we slide the upper part in rightward and the lower part leftward, you have a compression here, the bend. So it's increasing the normal stress here. And on the other hand, in releasing bend, the place tend to become tensile after many earthquakes because this part is rightward and this is leftward. So from theoretical analysis based on the linear elasticity, Romane shows that the change of normal stress is proportional to fault curvature and slip. So, but we want to avoid this very high or very small normal stress in numerical simulation to get some steady state and to it's physically unrealistic. So we want to avoid. So very common way in nonplanar earthquake cycle simulation is that they neglect change of normal stress. But it's also unphysical because actually dynamic rupture simulations for single earthquakes usually incorporate normal stress change, so detect the gap, and which have been shown to be very important in controlling rupture dynamics, like slip distribution or when the velocities or something like that. So what we need is a model with short time scale normal stress change, but ensure long time scale steady state of normal stress distribution on the fault. So what kind of physical process can accommodate normal stress changes due to fault slip of nonplanar fault slip? So if you look at restraining bend in real world, there is typically mountains like this here. So this is from Tibet, example from Tibet. So this means not just the main fault, the main structural fault. There are lots of secondary faults that is typically not just structural, but also deep slip fault to accommodate the deformation, accommodate the high normal stress to relax the normal stress, very high normal stress produced by this fault sliding. So in numerical simulation, like I'm doing using BEM, boundary element method, we cannot account for the deformation in your fault medium because we are only discretizing the main fault planes. So, but we want to account for fault deformation, how fault deformation affects the stress state on the main fault. So we imagine that. So maybe it's easy to just approximate the fault deformation as some relaxation term of the shear and the normal stress on the fault. So this is why we developed this kind of additional term into our numerical simulation of the cycle. So we simply assume that stress is relaxed toward uniform background stress with a characteristic time scale. So this can be seen as some type of viscoelasticity, but we are not arguing this is crystal plasticity or creep in terms of viscoelasticity. We instead argue that this relaxation term is kind of encapsulating the effect of many faults surrounding the main fault. The activity of the main fault can be approximated by this term. So the good thing using this equation is we can get steady state in normal stress distribution on the fault bend. So this is showing the normal stress value as a function of time over the earthquake cycle. So that we have statistically long-term steady state, but the normal stress is changing in short time scale during the single earthquake cycles. So the steady state is defined as the balance between stress increase due to fall to sleep and relaxation time. So this is the way we do earthquake cycle simulation using nonplanar world. So there are some other ways to do similar things, like Nielsen and Novo and Johan and Oglesby. Although they are not earthquake cycle simulation based on the latency prediction, but the idea is similar. So I'm now switching to the result. So the seismic cycle rate is, for this plot, I'm showing the slip rate on the board as a function of time and space time plot of slip rate. So you can see that there are periodic complete rupture of the fault system of the board. So this earthquake nucleate here and propagate upward, then break the total segment of the total fault. So in this reference simulations, there's no partial ruptures. So all ruptures are complete ruptures. But if you introduce bend on the board, the earthquake is more complex and its behavior is more chaotic. So there are many ruptures arresting at bend, but some ruptures are able to propagate through the bend. It depends on the previous history and initial stress at the time of the beginning of earthquake. So there's an additional interesting thing happening here, which is like this and this. So the time interval. So this is plot against time step. So there's no information about time in this plot. This is not, so this is actually not a good thing. But actually, the typical recurrence interval for earthquakes is 100 years in this system. But the time interval between this guy and this earthquake is only like a few hours to few months. Is the same situation for this. So you can, I can say that the rupture is actually continuing here, but just slowing down and becoming aseismic at the bend, at some barriers. So they can be activated again after some time. So they produce kind of aftershocks. So we speculate that this is what is actually going on in many foreshock and main shock sequence in the real world, like maybe Ridgecrest or Kumamoto earthquakes. So we are now doing some parameter study. So the most important parameter in this model is the angle of the bend, as suggested by the empirical law from observations. So as increasing the angle of bend, which is denoted theta here, you tend to get more probability of partial rupture. So this is comparing to 10, 20, 30, and 40 degree bend. So in 40 degree bends, all ruptures are partial rupture. There is no complete rupture in this plot. The situation is very similar in the case of releasing bend. So releasing bend has this structure, so that there's a lot of partial rupture and the ratio of which increases with bend angle. But one important difference between restraining and releasing bends is that in restraining bend, so there's a left segment and the right segment, and the rupture of left segment and the right segment doesn't overlap. So there is constant accumulation of stress here. So this is because rupture terminated before passing the center of the bend, like this. But for releasing bend, the region of the rupture region of left segment rupture and right segment rupture overlaps. So because they are terminated after passing the center of the bend, so they are overlapped, and there is no stress accumulation Yeah, because they are more frequently ruptured. So this difference can be explained by the sense of normal stress change. So in this restraining event, normal stress is increasing here. So the rupture is more difficult to get the center of the bend. But in this case, in this releasing bend case, the normal stress is actually lowest at the center of the bend. So it's easy to get to the center of the bend. But after passing the center of the bend, they tend to stop due to unfavorable rupture conditions, stress conditions. So this is one difference. So now I'm turning to the statistics. So this is showing the distribution of each earthquake created from the synthetic catalog of these simulations. So this is the strip distribution is like this. So by looking at this strip distribution, we divide these earthquake catalogs into three categories. One is passing rupture in blue. So this breaks the both left and right segments of the fault. And red ruptures, the red is for stopping ruptures, so which was arrested inside the bend structures. And black is other ruptures, so which doesn't have anything to do with bend. So we calculate the passing probability for each simulation, each prospective cycle simulations by this equation.
And can you remind us, where do the ruptures start? Do they always start at the ends?
Yes,
or?
they are mostly start at the end. So basically, we are only considering the event starting at here and here, and we are not thinking about.
Because otherwise that would make a difference too,
Yeah.
right? Depending on how much, where you start.
So we did this analysis for many different sets of parameters because there are a lot of free parameters in our model, like some frictional parameters, and also the width of bend can also be varied. So there are a lot of parameters. So I ran 500 or maybe 400 simulations using this different set of parameters, and each point corresponding to each simulation, each set of parameters. So there are a lot, so 400 points here. So as you can see, a single probability defined from this equation is basically a function of bend angle. And as increasing the bend angle, you tend to get smaller passing probability. So one interesting point is that there is an asymmetric structure. So the positive bend angle means restraining bend, and the negative means releasing bend. And in restraining bend, the drop of the passing probability with bend angle is more or less continuous. But in releasing bend, the drop is more abrupt. So there's some threshold bend angle, and at which the passing probability transition from 1 to 0. Although there are some cases for intermediate values.
Does your relaxation time make any difference?
There's no difference. There is little difference. So I have some parameter study using different type of parameters. So all of them doesn't show very clear patterns, like state evolution distance, realization time, with the location of the bend. So we can compare our results. So by averaging all the numerical results using 400 parameters, so you can take average and compare that with empirical from Bayes and Vesnovsky. So they are rough agreement without any tuning. So I think the result is very robust for many different type of parameters, and the result is basically determined by the angle. The bend angle is most important parameter governing the seismic cycle in this system. Also, this is 2D quasi-dynamic simulation. So another point is the cumulative slip on the fault is output in the simulation. It's not prescribed. So here, the extension of the fault they are slipping at constant rate, so they are imposed. But the cumulative slip rate inside the fault is the output, the spontaneously evolving from the interaction of stress dynamics. So they can be compared with observations. So typically, we have smaller cumulative slip rate on the bend, on the fault bend, due to stress relaxation. So this is also consistent with some observational work from paleoseismology perspective. So in this fault in Tibet by Elliott 2018, so they find that the cumulative slip rate, long-term slip rate, is tapered toward the center of the bend. So our simulation is also consistent with the observation. So like this curve corresponds to this curve in the observation. So this is the final point that I want to make today. So if you read the third edition of the textbook by Schultz, The Mechanics of Plastic and Protein, so he defined two different types of barriers. One is geometric barrier, the other is stability barrier for action propagations. The geometric barrier is like fault bend that I explored in this study. Stability barrier is also explored in many different types of numerical simulations like Kaneko et al. 2010. So they put positive A-B, which is velocity strengthening rheology in the fault system, in the overall velocity weakening fault, and running the simulation. And interestingly, the qualitative result is similar in the sense that we have partial rupture and full rupture depending on the many different parameters, and we have some spectrum from no barrier to permanent barrier, like in this plot. So in this plot, we have many different probabilities depending on the parameters. So in our geometric barrier model, the fault bend acts as a barrier because interseismic stress relaxed by relaxation term, so which prevents the location, the bend, from accumulating high stress, which is why we have a partial rupture. And in stability barrier, velocity strengthening region acts as a barrier because interseismic creep on this segment prevents the location from accumulating high stress. So the reason is, the mechanism is different, but their effect can be quite similar between these two different types of bends. Conceptually, different type of bends. So that's all what I want to say. So I just summarize. So in the first part, I performed aftershock simulations, assuming many small subsidiary faults in the damage zone of rough main fault. And we documented the importance of the fault roughness to explain the realistic distribution of aftershocks. And we also reproduced Ohm's law and aftershock migrations. So this, I didn't talk about this one. So in the part 2, we performed long-term simulation of nonplanar fault with stress relaxation method to avoid astrological stress buildup. And the bend angle is the main control of passing probability as suggested by the empirical rules. And the decrease of long-term slip rate due to the presence of bend is also observed in our simulation. So thank you for listening to my talk. I take questions.
Thank you very much. Do we have questions?
I have a question about these. When you showed the aftershocks clustering at the two ends, and as you increase the roughness, they decrease and they cut. I mean, when I think about aftershock sequences, I think about them being pretty even along the entire length of the fault. So how do you, what does that tell us something then about how rough the faults are? Could you use this to, how far could you push this model? Could you use this to say something about the overall roughness of the faults?
Yes. Yeah, that's important point. So I think this model is still simplified in the sense that there's only single rough fault, and the level of the degree of roughness is uniform all over the fault. Like, but if we have more rough fault, more rough, and this segment is less rough, you tend to get more aftershocks here than my expectation. So we can infer that the degree of fault roughness from the spatial variation of aftershocks is the one kind of prediction that I can make from this model. That answer.
Yeah.
Is your analysis of the bends meant to be scaled down to apply to the heterogeneity along faults?
Yes. So that in the second part, you mean?
Yeah.
So I think I have to be careful about thinking about the scales. So because fault geometry changes over time, actually. So in this simulation, so I assume for computational reason, the fault geometry doesn't change all over the 10,000 years, but it's unrealistic. So I think if you go to smaller scale, the fault geometry changes over smaller time scales. So I think it's not a good idea to simulate very small scale heterogeneity in this method for long time simulations, because it should change over time. But if you stick with relatively large spatial scale, you can run the assumption of the fixed fault geometry can be valid for a relatively longer time scale. That's my expectation. It's just very intuitive intuition.
I have just a fun comment. You mentioned Corona Heights in your. I don't know if you've had a lot of time since you've moved here, but you could probably get the Caltrain there. I guess if you're in Stanford, we'd get the bar, and it would be very.
Actually, I've been here.
You've been to Corona
3 years
Heights?
ago.
Yes.
Yes. Yes.
Do you get past the rock climbers that are there?
Yeah, I think there are a lot of climbers because it's very popular place for doing.
Cool. So
It
you've
was
been
3
there.
years
You've
ago.
been there.
So there was the AGU meeting in San Francisco.
Mhm.
So I visited Corona Heights Fort. Actually, but it's more convenient, not Caltrain.
Mhm. Yeah.
He's got it all figured out.
Yeah. Way back.
Yeah, because
Stanford.
this morning actually I was using the bus to come here. So I think I was I could get around here if I was very free.
Sure.
Anyone else who hasn't been there, it's pretty remarkable, isn't it?
Yeah.
It's beautiful.
Yeah.
Any other questions? I have one more. For the Wenchuan earthquake rupture, there was more slip in some of the stepovers and bends than elsewhere. And when you go back to your slip distributions, where you have there are a few events that have slip peaks in the bend, and others, this one.
Yes.
Right, there's sort of two populations of your passing ruptures. So this kind of reminds me of sort of the idea that you need both types of ruptures to ultimately make up the overall behavior.
Yes, it depends on what is the type of the previous rupture. So it depends on the history of the.
So the pre-stress is affected by the previous.
So,
Exactly.
yes, I think it's also very interesting to compare with observation. So in some, also there's a releasing and restraining event in Palu earthquake in Indonesia in 2017 or 18. So they also, it was supercell rupture, and there are some peaks and slip rate and slip in some releasing event, if I remember correctly. I think they also have some validation or something like that for this kind of physics-based models.
Great. So any other questions you have, bring them to the balcony and join us for drinks and pizza. Thank you so much again.
Oh,
I've never been.
you haven't? Oh,
No.
that's super shiny.